nothing beats this video. What we're going to do here is we're going to just roll through about 4 different examples of using the chain rule just so we can get that process down. The previous video on the chain rule, of course, came up with the rule, but now we want to actually use it. So let's go. So like I said, let's do some chain rule examples. All right, now we're going to find a bunch of derivatives here in a moment, but let's just quickly refresh what chain rule is. Remember, assuming that we have a function of the form, call it h of x is f of g of x, a composite function, and assuming that g is differentiable at x and f is differentiable at g of x, then the derivative of h with respect to x is going to be take the derivative of g, differentiate it with respect to x, and multiply that with the derivative of f and evaluate that derivative at g of x. So g prime of x times f prime of g of x. And of course, if we let y be equal to h of x, and we also let u be equal to g of x, then we can equivalently write dy dx, our derivative function, is the same as dy du times du dx. So all of that was talked about in the previous video. I just want to make sure we say it because now we're going to use it. Let's find some derivatives. So let's start with this function right here. E to the negative x cubed. We're going to differentiate that function with respect to x. So when we're differentiating composite functions, first thing we want to do is obviously note that, oh, we have a composite function we want to differentiate. But then once we identify the composite function, what's the inner function? What's the outer function? And so for us, we can think of our composite function h of x or f of g of x is our function here, e to the negative x cubed. And so we want to identify what's the inner function g, what's the outer function f. Well, in this case, g of x would be equal to negative x cubed, and f of x would be e to the x, so that if I replace the x in f of x with negative x cubed, I would get exactly this composite function here, e to the negative x cubed. So then what do? Well, a couple of things. One method, like we saw, is if we let u be equal to g of x, the inner function, which is negative x cubed here. Then our rule, right? H prime of x above, like we said a moment ago, g prime of x times f prime of g of x, or equivalently, dy dx is dy du times du dx. So what do we have to do? We have to find g prime of x, and we have to find f prime of g of x. Or if we prefer, dy du and du dx. So let's do that. Let's go ahead and try g prime of x first. Well, g of x is negative x cubed. So g prime of x is just going to be a negative 3x squared by our power rule. What else? Well, what's f prime of x? F prime of x, well, f of x is e to the x, so f prime of x is just e to the x. And so from here, we can find f prime of g of x by taking our f prime above, e to the x, and replacing it with the negative 3x, or excuse me, replacing it with g of x, which is negative x cubed, right? G of x is negative x cubed. So f prime of g of x is e to the negative x cubed. And thus, this derivative here is going to be equal to g prime of x times f prime of g of x, which is a negative 3x squared, there's our g prime of x, times e to the negative x cubed, which is our f prime of g of x. So that's one such way of approaching it. Of course, the other way of approaching it is by considering this variable u here is g of x. So we already know that g prime of x is negative 3x squared. And so we're going to see a similarity here. If I went ahead and just found f of g of x right away, so note f of g of x could be written as f of u here because we're calling g of x u. But what is that? Well, f of x is e to the x, so f of u is e to the u. And thus, it follows that f prime of u is also e to the u. And then if we went ahead and replaced u in terms of g, we will see that we get f prime of g of x is e to the negative x cubed. So we get the same thing. So that u method, if you will, is just really an alternative way. If we don't want to keep track of the g of x along the way, we can just replace g of x inside f with the variable u, and then differentiate f with respect to u, and then back substitute in u is g of x after we've done the differentiation. So either method is fine. How about another one? How about this one right here? This time we have this composite function, w squared plus 1 quantity to the negative third power. And we're going to differentiate that function with respect to w. So here the input variable is w. But again, we should think of this function here as like an h of w in this case, which is w squared plus 1 to the negative third. And let's think of it as some f of g of w here. Well, again, we got to identify our inner function and our outer function. So notice that g of w would be the inner function w squared plus 1, and f of w would be the outer function, which is w to the negative third power. So if I replace my w in f of w with g of w, w squared plus 1, I get our composite function. And then we play our game again. So what is g prime of w here? Power rule, that's just 2w. And then f prime of w, another power rule, is negative 3 w to the negative fourth power, differentiating f with respect to w. It then follows that f prime of g of w, which we need, is take our function, boom, and replace the input w with w squared plus 1, which is g of w. So we'll get a negative 3 times a w squared plus a 1 to the negative fourth power. Notice that again, if we let u be g of w, then we can interpret g prime of w as du dw, right? And f prime of g of w is really the same thing here, over here, as dy du if we thought about it that way. Doesn't really matter which way we think about it because it always gives us the same result, and that is the result that we get here. What is this going to be equal to? G prime of w times f prime of g of w. G prime of w is 2w times f prime of g of w, which is a negative 3 times a w squared plus 1 to the negative fourth power, which just gives us a negative 6w times a w squared plus 1 to the negative fourth power. So the more we do this, the more we get used to it, but we'll do a couple more here to wrap this up. Here's one more. This time we're differentiating t squared plus e to the negative 2t quantity to the third power with respect to t. So again, here's my h of t, which is some f of g of t. It is a composite function again. And we can identify our inner function, g of t, as t squared plus e to the negative 2t. And we can identify our outer function, f of t, as t cubed. So, g prime of t here, differentiate g with respect to the input variable t, is a 2t, and then minus a 2e to the negative 2t. Right? It's power rule and then derivative of a power of the natural exponential function. F prime of t is just 3t squared, power rule, but we need f prime of g of t. So replace the t in f prime with g. G was t squared plus e to the negative 2t, and we get a 3 times a t squared plus e to the negative 2t, right? Here is our g of t. And then all of that to the second power. Thus, our derivative that we get is going to be equal to, well, g prime of t times f prime of g of t, which is 2t minus 2 e to the negative 2t. There's my g prime of t, times f prime of g, a 3 times a t squared plus a e to the negative 2t quantity squared. Or if we prefer, we can write that 3 in front just so it looks a little more nice. 3 times 2t minus 2 e to the negative 2t times a t squared plus e to the negative 2t squared. It's a chain of derivatives, hence the chain rule. All right, we got one more to look at before we wrap up these examples. And that is this one. This one's kind of a little bit of a more of a monster because we have a product of two different functions. And each of the functions happens to be a composite function. So we're going to differentiate this function here. X squared minus 1 to the 4th times x squared minus 4 to the 5th. So the first thing we got to do, because it is a product, is we got to apply the product rule. So let's just write that out. First things first, what are we going to get here? We're going to have the first function, x squared minus 1 to the 4th, times the derivative with respect to x of the second function, x squared minus 4 quantity to the 5th. Product rule plus, all right, the second function, x squared minus 4 to the 5th, times the derivative with respect to x of the first function, which is an x squared minus 1 to the 4th. So then that's our first step, right? Because that's our product rule step. And then as we see, we have to find each of these individual derivatives, and each of those is going to entail a chain rule. And thus, what are we going to do? Well, let's just, for this one, keep track. All right, our composite function, think of the function there. Let's call that h1 of x is x squared minus 4 to the 5th, right? And that, of course, is some say f1 of g1 of x, if you will. So what's the inner function? g1 of x, the inner function is going to be x squared minus 4, and the outer function f1 of x is going to be x to the 5th power. And so we can find our derivatives here. g1 prime of x is going to be just 2x, and f1 prime of x is 5x to the 4th, which tells us that f1 prime of g1 of x is just, well, take my derivative, 5x to the 4th, and replace it with g. So that's going to be a 5 times an x squared minus 4 quantity to the 4th power. And thus, we can write out that first derivative, the derivative with respect to x of x squared minus 4 to the 5th is going to be g prime, g1 prime that is, times f1 prime of g1 right here, So 2x times 5, that's going to give us a 10 times an x, and then times an x squared minus 4 to the 4th. So that's that part right there, right? But we still have to find this other derivative to complete our entire process. And so if you will, let's focus on that. All right, for that second function, derivative with respect to x of x squared minus 1 to the 4th, we could think of that function right in there as, say, h2 of x. h2 of x, which is x squared minus 1 to the 4th power, or if you will, f2 of g2 of x. I mean, you can call these whatever you want. I'm just trying to keep track of them using the same notation, more or less, that we've been using. And so what's g? g2 here, the inner function, is going to be a x squared minus a 1. And then f2 of x, the outer function, is x to the 5th. Or 4th, should I say. Sorry. And so g2 prime of x is just 2x. f2 prime of x is a 4x cubed. And therefore, f2 prime of g2 of x is going to be equal to, well, again, replace my x in that derivative with g2, which is x squared minus 1. So that's a 4 times an x squared minus 1 to the 3rd power. And so that derivative right there is going to be equal to, well, g2 prime, 2x, times f2 prime of g2, 4 times x squared minus 1 cubed, which gives me an 8x, right, 4 times 2x, times an x squared minus a 1 quantity cubed. So we got our derivatives. We got that derivative, and we got this derivative, and then so finally, back to that red line on top, I'm going to replace my derivatives with what I just found. So let's go back down here, and we get that this entire derivative is an x squared minus a 1 to the 4th times that derivative we found in blue. So that's times a 10x times an x squared minus 4 to the 4th power plus the x squared minus 4 to the 5th power times that second derivative that we just found, which was an 8x times an x squared minus 1 cubed. So that's where we're at. That's our derivative so far. Now, it's a lot of stuff there, right? But you see how I'm keeping track of every little piece so we don't get lost throughout the process. Now, at this point, we've done the differentiation, and the only suggestion that I would say here is, well, let's clean this up a bit. All right? Notice that there are common factors all over the place. We have a common factor of x squared minus 1 cubed. We have a common factor of an x squared minus 4 to the 4th power. And then we also have an x sitting around. And we also have a common factor of a 2 on those two pieces. So I'll take all that out. I'll take out a 2 times an x. I'll take out an x squared minus a 1 cubed. And then I'll take out an x squared minus a 4 to the 4th power. What am I left with after I remove that from everything? From the first term, I'm left with a 5 from that 10x. Remember, I took out the 2x from there. And then I'm also left with an x squared minus a 1. From the second term, I'm left with a 4 from that 8x part. And then I'm also left with an x squared minus a 4. And so, almost done here. What do I got? I got a 2x times the x squared minus a 1 cubed times the x squared minus a 4 to the 4th. And then in here, I'm going to go ahead and just combine some of that stuff. You see there's some like terms. Got a 5x squared and a 4x squared. So that's going to give me a 9x squared. And then I got a minus 5 and a minus 16. So that's a minus a 21. And notice from here, I have a common factor of 3. So let's just complete this off. Take out that 3, multiply it with the 2x, and we get a 6x times an x squared minus 1 cubed times a x squared minus 4 to the fourth, and then times a 3x squared minus a 7 after removing that 3. And there we go. So that's a lot cleaner, I think, than the red statement above. So the last 3 parts are just some algebra, right? Cleaning up our result. But that's it. We found it. So this video showed us 4 different examples of using the chain rule to find derivatives of composite functions. And hopefully it gives you an idea of how to move forward on your own, try some on your own, and see if you got it down. We are going to have another part to the chain rule discussion here, where we're going to generalize the power rule for composite functions, and also situations where we have natural exponential functions raised to powers. Like, let's just generalize those rules overall. So that's what we'll do in the next video, among other things. And until we have that next video, you know what it is. It's Math and Beats, and I'm out of here.